Okay, let's look at our first projectile problem here. This is two-dimensional kinematics. The specific application is a projectile. So projectiles are free fall particles in 2D. That means that they're only under the influence of gravity. So we are not considering air friction. We don't have the math to consider other forces. We're just considering the only force on the particle is the weight of the particle. So this is the way a particle would move in a gravitational field. You should be familiar with this because you see this all the time in your life because you live on the Earth's surface. So this is a case here of a particle being fired off of the top of a table and then say impacting on the floor. This is, consider it to be happening in a house or lab or something like that. So nothing huge, just something that you can kind of wrap your mind around. We're given v prime, which is the launch speed of the particle. We're given h, which is the initial height there off the floor. And then we're given phi, which is the launch angle. And then we're asked to determine L, which is the horizontal range, as it's called, or horizontal displacement. We can call it too. So before I can really kind of get into this problem, I need to place a coordinate system on it. And in physics, a lot of the times we're being asked to analyze a natural situation, right? A physical situation like this one that doesn't come with a coordinate system. So part of our job in analyzing the situation is to place a coordinate system on top of it so that we can start doing some math to analyze it. So I'm going to do that here. A coordinate system consists of two things, an origin and a sign convention. In this case, we need a two-dimensional sign convention because this particle, we're following it in x and y. It might have a third dimension in there, but we're not taking that on for projectile motion. We're pretty happy to just be doing two dimensions here. So I'm going to let my x be positive to the right, positive x to the right, and then positive y downward are going to be my choices here. So I'm using X for horizontal and Y for vertical. Those are conventional choices, and they're choices that will communicate best. It's best to choose conventional choices as far as, yes, you could pick Y to be horizontal and X to be vertical, but it'll be harder to communicate your ideas that way because it will not really be expected. When it comes to sign convention, though, that is up to you and think about what might be advantageous for solving the problem. In this case, I see that my x displacement and initial velocity are both directed to the right. So in order to have both those quantities positive, I'm going to make rightward positive. For my vertical, I see that I have an upward initial velocity, but I also know that both the acceleration and then the displacement are directed downward in this problem. The projectile ends up at a lower point than it started, so the y displacement is downward directed. So I'm going to choose a positive y downward for that reason. So that's my sign convention. I also need an origin. I'm going to go ahead and set my origin right at the launch point, and I'll need to label that origin 0, 0, 0x, and 0y. Remember, this is two-dimensional here. So that allows me to get started. Notice what we're given and what we're asked to determine. The first thing I'm going to do here is break up my initial velocity v prime into its x and y components. So remember about projectile motion here that we have x and y, but they are independent of one another. They don't affect each other. They have completely different displacements, velocities, accelerations that don't affect each other. So it's really important right off the bat here to take that initial velocity and split it up into its components because we're going to need to know what is the initial velocity in the y and in the x. So I'll go ahead and take that v prime here. I won't always do this as a separate little calculation, but maybe just for this first time. Take that v prime. Here's the angle phi, and I'm going to split that up into components. I'll change my color when I'm doing that. So here's going to be the x component, right? That's going to be the x component there. That's v prime x, which in this case is equal to v prime cosine phi. Can use SOHCAHTOA there. And then I have a y component, of course, that's directed upward there. And That is my v prime y, which I can express as v prime sine phi. Okay, so I've got that split up. Again, I need those separated because I'm going to be doing my analysis separately here. So when you're working these projectile problems, I think it's really useful to completely separate on your paper, right? Separate your x and y motion. If you have them together, like all together on your paper and unseparated, they're going to be really jumbled in your mind as well. So the organization that you keep in your work, that is helpful for someone else that's reading your work, obviously, but it's helpful for you too. And your brain learns from pictures. All of us, our brains learn really quickly from pictures. So when we organize things, when we space things out visually, that helps us think. So I'm going to start putting I'll put the X motion, that's horizontal here, and everything I know about that there. And I'm going to write everything I know, my knowns, the Y motion here. Note that in the homework format, we really want you to be always writing your knowns and unknowns for each problem, and I'm going to follow that here. We'll do the same thing. So for the X motion, what are things I know? Well, the initial position is equal to 0 because of where I set my origin. The final position is equal to L, which we don't know, right? We want to determine that. So that's the thing we want to find. My initial velocity in the x, well, that's rightward directed, so it's positive. I'm going to go back up to this velocity vector diagram here, and I'm going to remind us what our sign convention is. So rightward is positive x, and downward is positive y. So let's remember that. So my v prime x is actually positive value. I need to consider that when I'm writing this down here. V prime cosine phi. So both the L and the V naught x, the V prime cosine phi are positive due to the sign convention. A sub x, the acceleration in the x direction is of course 0. This is a projectile. If you're not familiar with projectiles yet, you shouldn't be watching this video. You should be doing the reading first and the lecture videos first. Okay, Y motion. Y naught is equal to 0. Again, that's where I've placed my origin. The final position for y is this impact point, and that is going to be h below the origin. And notice that I have positive y downward, and my displacement is downward, so that's going to be a positive h. My initial velocity in the y is directed upward, so that's the negative direction for y. So that's going to be negative v prime sine phi. And my acceleration in the y is directed downward. It's equal to g positive because downward is positive. So as you're filling these out, when you're doing these kinematics problems, really important to remember that we're still talking about vectors here. You must consider the direction for this stuff. So one thing you can do if it helps you is kind of go through and draw. You can even think about this visually and think, well, okay, like if I'm looking at my y stuff, I know that h, for instance, is measured down from the origin, right? So I know that's going to be positive. My v naught y is pointing upward, so I know that's going to be negative. My acceleration in the y is directed downward, so I know that's going to be positive. Okay, you can go kind of through that for yourself. Everything in the x here, both the x displacement and the x initial velocity, those are both directed to the right, which is the positive direction. Okay, so now I've got the stuff that I know here, and I have it written in terms of the problem. So something that I'll often say to start with is like, just express the thing you're being asked to determine. Like we're being asked to determine L here, right? So, what if I just try to find that right now and see, can I fully express it? If not, what else do I need? It'll help give me direction in how I should proceed through the problem. So, I'm going to go ahead and do that. Just try to express L. And I'm going to start with a general equation here. X final equals X initial plus V naught xt plus 1 half AT squared, A sub X t squared. So this is position with respect to time. It's one of our kinematics equations. And specifically, it's position with respect to time in the x. Notice that we always start with the general equation. This is the general equation. And then we customize that depending on our particular situation. So I'm going to customize it by looking over here at what I figured out for my x motion over on the left hand lower left side of the page. So x final is equal to L, right? X initial is equal to 0. V naught x is V prime cosine phi. That is multiplied by t plus 0. That last term is 0 because a sub x is equal to 0. So I'm left with L is equal to V prime cosine phi times t. I'm careful with those parens because I don't want to smush the phi and t together and make it look like the argument of the cosine is phi t, right? So be careful about that when you're using trig functions. Great. So what does this show me? This shows me that I'm not done, that L is something that I want to find, right? V prime, I have, that's given. Phi is given, so I know everything in the parens there, but I need to express T time. T is not given, right? So I need to express that. So now is when it can be useful to look at the Y motion, because the one thing that your horizontal and vertical motions have in common is their time, right? They don't affect each other in any way, the X and Y, but they are both taking place at the same time. So we can take advantage of this. We can leverage what we know about the vertical in this problem in order to use that to express the time. Once we have that expression for time, we can substitute it back into this equation for L. So it's nice that we have this. This is an important equation. We're just not done, right? This equation here for L. Now we know that basically we need an expression for T. So we're going to move forward and analyze the Y in order to do that. So I'm going to do the same thing now in the Y. I'll use position with respect to time. Y final equals Y initial plus V not YT plus 1 half AYT squared. Again, this is my general equation. I'm now going to go back to this Y motion list that I made earlier, and I'm going to use that to fill in that general equation there. So I can do that. And that'll give me H is equal to 0 minus V prime sine phi times t plus 1 half GT squared. Okay, I can rewrite this 1 half GT squared minus V prime sine phi times t minus h is equal to 0. And then I can use quadratic formula. Yay. So when I do that, I'm going to skip at least one step there. You can see the gory details in the written solution. What I end up with is something that looks like this. T is equal to V prime sine phi, and I'm going to say here plus or minus, because I want to talk about that, root V prime sine phi squared plus 2gh, and that is all over g. So, sometimes I know when you're doing a math problem, you can kind of get away with leaving the plus or minus, like, oh, hey, there are two possibilities here. Not so much in physics. So, in physics, you need to analyze your situation and ask yourself if both of them are really do really make sense. And in this case, you wouldn't really actually expect to have two times, right? Let's go back and look at our scenario real quick. So this is a projectile that's fired off a table here and impacts on the floor. I mean, there's going to be only one time that you should be able to get out of there instead of two possibilities, right? So if you wonder what's going on here, first of all, you can think about which one you should pick, which one would be physical. Only one of them is going to be positive, right? Look at your values there. It's one of the neat things about doing this symbolically is you can really see what's going on and what is affecting our value of t here. But I can see since the second term in the numerator is greater than the first term in the numerator, that if I choose a negative sign, it's going to give me negative time, which is non-physical. So I would need to choose the positive value of time there. And if you're asking yourself why, what's that about? Like, is that just a throwaway thing, having that negative value of time? Not really. What that's about is the fact that the equation for a projectile is going to give you something that looks like this, right? The whole projectile arc. But in our problem, we launched the projectile right here, right? We launched it from a particular point, from a particular height h. So this stuff all here is non-physical for our case. Mathematically, though, it's part of the same equation, isn't it? It sits right there in that quadratic. But we know that because the particle was launched at t equals 0 and we're trying to find the flight time, that that negative solution would be non-physical. So this is just saying that I want you to kind of have some understanding as far as where that negative solution comes from mathematically, and also be able to toss it out and know that it's not something that we're going to be thinking about because it's not physical. Okay, so now we have t. Yay. I'm going to change colors. So now we have t. Now that we have our expression for time, I can then substitute that back into the on the other page where I had my expression for L, and that's awesome. So L then is equal to, let's go back and look at that real quick, is equal to V prime cosine phi times t. So that'll be V prime cosine phi times this expression for t, which is going to be V prime sine phi plus, I know I'm using that positive sign there, root V prime sine phi squared plus 2gh all over g. There we go. So that is my final expression in terms of givens for L, because we were given phi, we're given V prime, and we're given h. G is a constant, so we can consider that to be given. When you arrive at your final expression, symbolically like this, and I always advise that you do homeworks like this and then you substitute your numbers in afterwards. That's in our homework format suggestions as well. Check out, do the dimensions work? And it's not that hard in this one to figure out if the dimensions work. You know you're looking for length dimensions since this is a displacement that you're finding. Does it make sense that the answer would be positive? You can ask yourself that question. And if you want to, if this problem you were like, wow, okay, I think I could barely get through this, and you want to spend more time on this problem, like any problem, you can do it over and over again. My advice is, though, so you're not memorizing stuff, do it, change the origin and work it again, change the sign convention and work it again. Really kind of go through those different reps of just changing some superficial things, making sure that your physics is, straight on every single time, and you should always get the same value, right, for your answer. If you change up your signs, then your displacement might end up being negative, depending on what your sign convention is. So, keep track of that. But practice, practice, practice is how we get good at anything, including this.